say that X has n elements. This is the definition. In this definition only we have defined rigorously what having n elements means. Okay. If X has cardinality n, we denote that fact by writing okay. We put a hash before the set, and that denotes the cardinality of the set. There are other notations for this thing, and you may have come across two of them. This also sometimes denotes cardinality of X, or O of X, order of X. This also sometimes denotes cardinality of X, provided X is finite. Although we have not yet, we haven't said anything about finiteness yet. We are just simply saying that if X is a set and n is a natural number, when we can say that X has n elements, or the cardinality of X is n. That much only we have said so far. So this is the definition. And then there is a remark. Since the set of all natural numbers lying between 1 and n, where n itself is a natural number, has the same cardinality as this set, as the set of all natural numbers strictly less than n. We can use the set in the above definition instead of this one. So here a small question arises. We are saying that these two sets have the same cardinality, but what is the bijection? So this I leave to you. You try to figure out. It's not very difficult. I suggest you make this as the domain, this as the range, and use the increment operation to define a bijection. You should be able to do this. Okay, so instead of using this set can also be used in the above definition, in that definition, because they have the same cardinality. Right. Now Next comes example 367. Let A, B, C and D be distinct objects then this set has the same cardinality as this set, okay, and both of them have cardinality 4. This set has cardinality 4 because there is a bijection between this set and this set when n is 4, and this set has cardinality 4 by definition, okay, and because every set has the same cardinality as itself, that's why. Similarly, this set has cardinality 1 because there is a bijection between this and this set. Okay, in place of n we have 1 here. You can easily prove a bijection, but now we come to an issue with this definition. We may have a problem with definition. I keep forgetting these numbers. 364, I think. Is it 364? No, 365. A set X that has cardinality n may also have a different cardinality m not equal to n. You see, if you look at definition 365 carefully, when we say that X has cardinality n, when X has a bijection with this set, that's it. If you find a bijection between X and such a set for some natural number n, we say that X has cardinality n. But the definition is not stopping us from having the possibility that at the same time X may also have a bijection with this set. where m is different from n. That may also happen, because then by that same definition x should also have cardinality m. So in that case it will have two different cardinalities. We will now have to show that, first of all, that does not happen actually. Once a natural number has been assigned to a set as its cardinality because there is a bijection, then it is unique to that set. That's the thing we are aiming to prove next. So you see that our simple conceptualization of number of elements in a set is after all not that easy. I mean, we have defined it using bijection, but we have to prove that it is unique, and it's not obvious at all. Okay. But this is not possible. Because of the this proposition. Okay, these results and definitions seem to come with some names also, so that we can refer to them later when we need them more easily. This one is called uniqueness of cardinality. So that later when we need this result somewhere, instead of referring to it like proposition 368, which does not convey anything other than the fact that there is a proposition and who knows what it says. But if you say uniqueness of cardinality, then that immediately tells us what it's about. Some others are also there that I have forgot to mention. In the definition of two sets having equal cardinality, you can write equal cardinality within brackets. And in the definition of cardinality, I think there is nothing, no. Okay. So let X be a set and let X be a set with some cardinality n, where you should understand that because we have said cardinality, n is a natural number, then X cannot have a cardinality m where m is different from n. Okay, now this is a very important proposition and we will prove it, but before we prove it we need a lemma which will be used in the proof. Okay, so before we prove the above proposition, we need the following lemma. Let n be a positive integer. Oh, okay. I cannot write integer because we haven't yet defined integers. We only have the system of natural numbers, so we have to work with them. I should not make a mistake like this. If I make somewhere inadvertently, you try to rectify it. Let n be a positive natural number. Yes. And let x be a set with cardinality n. So n is a positive natural number and x is a set with cardinality n. Then the first conclusion is x is non-empty. And for any element x belonging to x, the set obtained by removing that element from x has cardinality n minus 1. Okay, so that's what the lemma says. If x is a set with cardinality n where n is a positive natural number, then first of all x has to be non-empty, and if you remove a single element from x, then the resulting set has cardinality n minus 1. Okay. So now let us look at the proof. And the proof okay, let us see what happens when if x is empty, say. We have been asked to prove that x is non-empty. Suppose x is empty, then x cannot have the same cardinality as this set. Which is non-empty. Why is this set non-empty? Because n is a positive natural number. So we can have, because n is a positive natural number, 1 belongs to this set. Whatever n may be, 1 always belongs to this set. Why? Because of this inequality. Okay, and 1 is always greater than or equal to 1, so that's why 1 always belongs to this set. Anyway, this is a non-empty set and x is an empty set, so there is no bijection between the two, and that is also following from something we have done before. Specifically, why we cannot have a bijection? that has been answered here, and we did this. See the solution to exercise 333. In this solution, we have seen what happens when we have function going from the empty set to some other set, namely the empty function for a given set x or for a given range. When is an empty function bijection? Okay, so that thing has been answered here. So because of that, we cannot have a bijection. Hence, and this contradicts our hypothesis, because we have been said that x has cardinality n. That means x has a bijection with this set, and that is not possible if x is empty. So that means x has to be non-empty. Hence, x must be non-empty. Okay, so that we have got the first conclusion. Okay, now next let x belonging to x be any element. Next, we have to prove that if we remove x from x, the cardinality decreases by 1. Since x has cardinality n, there is a bijection f from x to this set. Because that is the definition of having cardinality n. There is a bijection. We now define a new function g from x minus x to this set. As follows. G of y, where y is an element here in x minus x, is defined to be equal to h of, okay, what am I writing? It is f of y if f of y is less than f of x, and it is equal to f of y minus 1 if f of y is greater than f of x. We have a lot of explaining here. First of all, there is no doubt with this one, but now we have sort of defined a function like this. Okay, so if y is coming from x minus x, then y is in x and y is not equal to x. Note that f originally is a bijection. That's why, since y is not equal to f and y is not equal to x and f is injective, this implies f of y is not equal to f of x. So either f of y is less than f of x or f of y is greater than f of x. If fy happens to be less than fx, then our definition of g of y is just fy. If it is greater than fx, then this is the definition. But by now I think you have seen that there is a terrible mistake in this whole thing. Do you see that? Have you noticed? N minus 1. What is this minus? We haven't defined anything called subtraction in the system of natural numbers. So what is this minus doing? It is actually a wrong statement, or rather not wrong but a premature statement to make at this stage, because we don't know about subtraction yet, and the theorem statement or the lemma statement is given like this in the text. So this is a small mistake that Tao has made, and we are now going to rectify that mistake. Note that the expressions n minus 1, also here fy minus 1, are meaningless unless we of course assign some meaning to them. We define n minus 1 and fy minus 1 to be those unique natural numbers for which the successor of n minus 1 is n, and just like that the successor of fy minus 1 is fy. But the question is, does there exist a unique natural number whose successor is n, and for that matter, does there exist one whose successor is fy? And the answer is yes, and the justification comes from something we did way back when we were developing the system of natural numbers. Note that existence and uniqueness of these natural numbers is guaranteed by lemma 2 to 10. 2 to 10 I think, let me just, yes, in lemma 2 to 10, if you recall, although it was a long time ago, the statement was like this: if a is a positive natural number, then there exists a unique natural number b whose successor is a. That was the statement of lemma 2 to 10. So in place of a, if you consider n, then you get be as n minus 1. That's what we mean by n minus 1, where this minus has no significance of its own, and like that fy minus 1. Okay, so the symbols now have got their meaning, but we have to now first of all show that g is well defined. We have defined a function, partly defined, however it is fairly non-obvious and somewhat complicated, involving symbols like that. So we have to make sure that what we have done, it has some meaning, it makes sense. Okay, note that, or let us proceed like this. Let y belong to x minus x, since y is not equal to x and f is injective, f is 1 to 1. So fy is not equal to fx. Thus fy is less than fx or fy is greater than fx, and this itself is coming from trichotomy, which also was a result that we proved about natural numbers. Okay, now we first look at the case when fy is less than fx. If fy is less than fx, then okay, now you see f itself is a function from x into this, so that means fy is a natural number lying between 1 and n. Then fy is a natural number satisfying this is there because it is happening, fy is less than fx. Under that condition we are looking at this case. Now fy being a function like this will lie between 1 and n. At the same time fx also lies between 1 and n, because originally x was there in x. Now we have removed x from x, that is a different thing. So that's why fx also lies between 1 and n. So you see that fy is greater than or equal to n and strictly less than n. This implies, or then or n minus 1, where you have to understand that n minus 1 is that natural number whose successor is n. From elementary properties of natural numbers that we proved before, if this happens then this happens, and conversely also if this happens then this happens. So you see that fy defined like this actually lies in this range between 1 and n minus 1 as a natural number. So this part of the definition has no problem, and because f itself is well defined, for that given y, fy is unique. Thus gy equal to fy belongs to this set, belongs to the range of G. What is the other case? If this happens, then Fy minus 1. So we will look at that one also. We can write it like that. If Fy is greater than Fx, then 1 less than or equal to Fx, that is less than Fy, and Fy itself is less than or equal to n, and hence one less than or equal to Fx, this is less than or equal to Fy minus 1, which is less than or equal to n minus 1. Okay, so if we look at the element or the natural number whose successor is Fy, then that becomes less than or equal to n minus 1, and because of this strict inequality, this now becomes less than or equal to Fy minus 1. So in this case, again G of y, by definition now this is Fy minus 1, it belongs to this set. And here also Gy is unique. Thus G is well defined.